Here lies a lonely iron nucleus, composed of protons and neutrons, which are collectively called nucleons. If you pull off a neutron, that takes a little bit of energy. You see that light blue flash? That shows endothermic, bond breaking. You could also pull off a proton, which is also endothermic, bond breaking. Now the energy that it took to remove those particles, for each one it's called the binding energy per nucleon. And of all the nuclei on the periodic table, iron has the highest binding energy per nucleon. Of course, if you put back the nucleons, then it releases the same amount of energy, the binding energy per nucleon. So what about the entire nucleus? Well, if you take all of the nucleons and pull the whole thing apart, that's the binding energy. And in this case, it's endothermic. Energy would be required. But if you put them all back together again, that's exothermic. Energy is released, the so-called binding energy. As the nucleons go back to form a nucleus, they will release energy. So the IB definition, the nuclear binding energy, delta E, the change in energy, is the energy required to separate a nucleus into protons and neutrons. Now that's going to take a lot of energy, so you're going to have to put energy in to do it. It's going to be endothermic. Take a look at the graph. This is binding energy per nucleon. So pulling off one proton here, one neutron there, not pulling the entire nucleus apart. And note that, as I said, iron has the highest binding energy per nucleon. It's harder to pull a nucleon off of the nucleus of iron compared to every other element. It's the hardest. So it's the most stable. Iron is the most stable of all the nuclei that have been found. Why is that? Well, because it needs the most energy to pull off protons and neutrons. So who cares? Well, all the nuclei in the universe are trying to lose energy. Oh, I got a message. Are trying to lose energy to become more stable. In fact, the whole universe is trying to dissipate all their energy to make it become more stable. And there are two possibilities for atoms. The light atoms, for example, hydrogen, helium, lithium, these lighter elements will fuse together by fusion. And the product of that fusion is going to have more nucleons in the nucleus. And the more nucleons in the nucleus, well, the more stable the nucleus will be, up to iron. So if you can approach the number of nucleons in iron, you're going to increase the stability of the nucleus. Now, the products of this reaction are lighter than the reactants. There's a missing mass, the mass defect, and that turns into energy, E equals mc squared, and this explains why the sun is so blinking hot. So on the other end of the graph, how can the nuclei there approach the number of nucleons that iron has? Well, they could undergo fission. Fission is breaking apart a nucleus to form lighter nuclei, and these lighter nuclei are going to be approaching iron in terms of their numbers of nucleons. Now, once again, the products of this reaction are lighter than the reactants. There's missing mass, the mass defect, and that turns into energy, E equals mc squared. It is indeed the binding energy. And that explains where the energy from nuclear bombs and nuclear power stations come from. So fusion and fission allow lighter and heavier nuclei to either combine or break apart so that they can approach iron on this graph. Now, one thing that looks a little confusing is that iron seems to have the highest energy. High energy, well, surely high energy is unstable. No. Iron is the most stable nucleus. Why is that? Because it takes so much energy to break it apart. Something like uranium is less stable. Why is that? Because it takes less energy to start pulling bits off it. It's pretty confusing, isn't it? I wonder if I made this clear. I hope so. So in astronomy, they have a saying, iron kills stars. Once you've undergone so much fusion that you've produced iron, nothing else is going to happen in terms of fusion, because you've reached the most stable nucleus possible. And fusion is moving lighter elements towards this stability. So I suppose if you leave a nuclear reactor for long enough, you might also get iron as well. I'm not really sure about that.